area. Chapter 6, Gavin and Dean, welcome, welcome. Anybody who's gone today? Jacob's gone, huh? Yeah. We are starting Chapter 6, Section 1. The homework is due tomorrow. How? Well, it has to do with estimating with finite sums. Meaning, n equals 5 rectangles, 4 rectangles, 7 rectangles, 10 rectangles, 2 rectangles. All I'm saying is rectangles because trapezoids are at the very end of Chapter 6 and not yet. Oh, that's nice. No trapezoids. What question does area under the curve answer? How instantaneous changes. Instantaneous changes. Those are instantaneous rates. How instantaneous changes could accumulate over an interval to produce the function that describes the total change. There's a lot packed into that statement. Basically all of the fundamental theorem of calculus. Accumulating nothing to produce something. The philosophical debate to the entire underlying use of infinitesimals in the beginning of calculus that almost got it. To never come into. Well, no, it was going to come. It was going to come no matter what. But the church was sure trying to stop it. AJ.
Can I ask a very off-topic question?
Do you think Dean or Gavin wants to hear it?
Probably not.
Okay, then I'll pause it for them. Below, the illustration says, a ship moves along. Bloop, 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 bloop. An ocean at a steady rate of 7.5 nautical miles per hour from 7 a.m. to 9 a.m. What is the total distance traveled by the ship? Why is there a rectangle drawn? It's the velocity function. Ooh, it's a constant velocity function, right? My physics people, you should have a better understanding of this than anyone else in the sense of position graphs, velocity graphs, acceleration graphs. Here is your velocity. True? Okay. So when, once upon a time, we had something called distance equals rate times time. If you have a constant rate, you can multiply that times time to get distance. That's one way of thinking about how to do this problem. But the other way is, well, this is easy. You just have a constant rate of 7.5, and how many hours is it traveling? Well, from 7 to 9 is 2. All you have to think about is an area of a rectangle, and the area of the rectangle is 2 times 7.5. Assuming all the units match up. Do they? Yes. Because I have miles per hour times how many hours? Am I going to get my 15 miles? So is there a geometric way to solve a distance equals rate times time problem? Yeah. Just call the area of the rectangle. So when you are doing distance equals rate times time, you are actually doing just the area underneath 7.5 in between 7 and 9, which is 2 hours. Maybe that's a good way to introduce this whole idea of area under the curve. That numeric value giving us a change in the antiderivatives. So with all of that, you guys should have this written down, yeah? What if I give you this one? Ready, set, go. Try to think about it with area. Is this simpler or harder than the one we just did? Yeah, because what's true about the rate? Velocity is not constant, right? Because what happens as soon as the ball gets thrown up to that initial velocity of 60 feet per second? If it was constant, that ball would keep on traveling up, up, and away and never come back down, right? But it's not going to stay 60. It's going to decrease all the way down to 0 and then turn negative because of what else is acting on it?
Acceleration.
Bummer, man. So how do you answer how high the ball goes? You start off with the acceleration. What do you mean? Acceleration isn't constant?
Yes.
So what do you need to go backwards to velocity then?
Oh,
anti-derived, something we haven't done yet this year, right?
Plus C integrate.
So we have negative 32, but then plus C, yeah, okay. So integration becomes necessary. We have our initial, and then we have our position. Now technically, you guys know that you totally learned this equation in pre-cal, right?
Yes.
Because you guys did motion problems multiple times when they would give you a free fall model and there were equations for position, velocity, acceleration that you could have memorized. Man, my voice is dying, sorry. Without using integration or differentiation. So in some ways, yes, you could say I'm integrating because you guys know where these equations come from. Or I could just be like, oh, free fall model from pre-cal is a thing. Right? But the dilemma is it as simple as? Is it as simple as a rectangle? Well, no, but isn't it still a geometric shape? Aren't I starting at 60? And what am I doing? I'm dropping, right? Every time another second passes, because of gravity, isn't my velocity going down at a constant rate? Check it, my velocity graph is just a line with a slope of negative 32, right? So then what do I know? Or what am I supposed to find? How high the ball will go. Well, how high? Hold on. Wait a minute. When does the ball stop going up and start going down? We should know this from motion even without using integration. When velocity equals 0. So can't I go ahead and say, okay, how high will it go? Well, it's going to stop when momentarily stop before heading back down, aka be at the peak of its motion. Subtract the 60, divide the negative 32, and t is going to end up equaling. Yeah, 4 goes into both. Does 8 go into both? No, I think just 4. Goes in 15/8 of a second. You guys agree?
Would it be the same if the question had asked for the maximum height?
Yes. Yes. So therefore, I could go ahead and say, well, hold on. At 15/8 second, it's not back on the ground yet. Well, wait a minute. Hold on. What's velocity? At 15/8? Oh. Because velocity goes from positive, hits 0 at the top of the motion, then goes negative. Where's the relative max if this is a graph of velocity? Isn't the relative max, AJ, I'm glad you brought it up, isn't it right here? See it? So velocity is positive, then 0 at the top of the motion, then it comes back down. So technically, what do I need to do? Just find the area of a triangle. Wait, I thought we had to find the max and then be able to plug back into the function and then, no, it's the area of the triangle. We just figured out this happens at 15/8. To change in position, well, hold on, how high does this go? Oh, 60. That's easy. 15/8 times 60. That's it. Well, that's the change in position, right? So technically, don't I have to start at where it started? So it was 6 feet. I have to start at the initial position, and then the triangle will give me how much it changed, it meaning position. So therefore, I have 60 times 15. Throw feet on there. How high does it go? Oh, but wait, how do you take the area of the triangle? Oh, bummer. What did I do? Area of a rectangle. So I guess I could make it a little bit nicer. There has to be 1/2, sure. But then we have it. Now that wouldn't be a nice, pretty answer. You should probably get to 30, and then you should probably maybe reduce a little bit, and then multiply and then simplify. But what is that going to end up being the exact same thing as? Plugging 15/8 into that. Area can give us what we need. If we have the graph of the rates, right? The graph of the velocity. Now, what made us able to do geometry in both these pictures? What was velocity in the first one? Constant. It was a flat line, true? What was velocity in this one? Wasn't constant, but what was it? Linear, which means geometry was still totally able to be used, but what's going to maybe happen in ones in the future? Oh, I keep on adding extra pages without needing to. I'm sorry. Hey, where did this curve? That's where Raven's thumbs come in. Oh, gravity. Maybe 32 feet per second. But technically, if we hadn't learned this yet, I would have reminded the calculus kids. Oh, so then you're thinking 9.8. Yeah. But it is interesting sometimes, maybe for me more so than for you, but like what if I was teaching you this for the very first time and I was getting you from pre-cal? In public schools, you have kids that have been in honors algebra, honors geometry, honors pre-calculus, to where, because of all the honors classes, they are able to do basically Calc AB for an entire semester, their honors pre-cal year, because they've gotten so far ahead. Our school obviously only does honors pre-cal because of partially teachers, partially student demographic, etc. So I'm not able to get you guys near that far ahead. We definitely go into more depth in Chapter 12 with limits and introductory power rules and some product quotient rules in pre-cal. But in other schools, you might have gone straight into BC because you would have done a semester of calculus in honors pre-cal. But it's interesting with this book. If I was just teaching you this for the very first time, you had never found an antiderivative. You had never done integration, how I would have done that last example. I would have reminded you of the free fall model from pre-cal word problems of -16 t squared, assuming we were in feet per second, plus initial velocity t plus initial position. Then we would have taken the derivative to get velocity. Then we would have graphed velocity and done the area problem that way. I wouldn't have started with gravity. I would have started with an equation that you would have seen in pre-cal. Anyway, interesting for me to think about, maybe some of you too. What if we had never learned calculus and we were seeing some of these things from this book's perspective? But what you guys are doing now is you are drawing rectangles underneath a curve, because velocity is not always constant and it's not always linear. Rates are not always constant, are not always linear. So what if they are curved? This one looks kind of like a cubic function, but we know it could be all sorts of different stuff. If area is the key in some way, shape, or form to unlocking from rates changes in the quantity that's changing, changes in the original function, well, we're still going to use rectangles, but rectangles in a way that approximates. Rectangles in a way that approximates the change. Riemann sums, we got that. We take a certain interval, cut it up into equal subintervals, that's our delta x. Delta x, we saw if we are able to make it ourselves, we can go ahead and do that nice little even distribution or that even division. Just take the distance between the end and the beginning, cut it into n subintervals. The actual area is going to be approximately us. Wait a minute. Why is there a sigma? Sum of, and who are these guys? Heights and bases. Oh, heights and bases. Those are rectangles, right? So the first rectangle, the second rectangle, the third. We could even put little delta x sub I if they change. But I just said that we're going to at least for most of them, if we're making them, we'll make them equal, so it doesn't really matter. The delta x is going to be the same. But in certain AP problems, they might make it so the delta x changes. But if we were coming from the left, I can't really say in this one if it would be an under or an over, because I have the function sometimes increasing, sometimes decreasing, sometimes increasing the concave up and concave down intervals. So right off the top of my head, there's no easy whether left would be over or under, whether right would be over or under. But there is notation as far as how we would show this. For instance, if we were coming from the left, we would go ahead and still be thinking about our n rectangles. That's still the same. But if we were coming from the left, we would have to go ahead and start at A. Because remember, A is sometimes 0, but A could be sometimes somewhere down the road. But the example we just did was between 7 and 9. A wouldn't have been 0, A would have been 7. So we would have to go ahead and start at that A. And we would have to add R B minus A all over N, whatever the length is of the subintervals, times I. But if I was to start at I would want to start at 0 because I have to start at A itself. So sadly, not even I works. Instead, we would have to do times I minus 1, which is even a little bit trickier. And then we would have our delta x, which would technically be our b minus a all over n. From the right, it'll actually be a little bit easier because from the right, we actually get to start not at A, but 1 away from A. In which case, we could just kind of do that little times I and not have to do the I minus 1. I minus 1 says, wait, not yet, start at A. Okay, now go. But from the right, we're actually like, no, go ahead and start 1 away. That's good. Now, last year, I didn't really make you guys make the Riemann sums because we didn't actually ever solve, I don't think, an integral using the definition of the integral. We just saw the Riemann sum, the Riemann sum definition of the integral. Now, don't worry. What is section 6.1 called? Finite or infinite? Finite. Okay, so we're not going to be doing the actual infinite Riemann sum right now. I'm just showing you how you would set up coming from the left and from the right. And can you guys see which one looks easier just by a quick perusal? The right one does, because it doesn't need the I minus 1. So if we were to choose, and if it didn't matter, we would totally be coming from the right. Whoa! An FRQ just showed up on the screen? Why? What part of this FRQ needs a finite sum to estimate an area? Ready? Set? Check it. What part of this FRQ needs a Riemann sum? Because what's letter C? Why am I narrowing out letter C and saying there's no way it's letter C? Because letter C is a related rates problem. Oh, that's like applications of derivatives. That's like shocking. Finding the volume. Wait a minute, the volume. Average value, there's a formula for, right? Because average value is in this radius, and they want the average radius. Wouldn't that be my 1 over, I know we haven't done it yet this year, but wouldn't it? Okay, wait, that would be an integral. Okay, so hold on. Maybe it's not letter A. That's like a normal integral problem plugging into a formula. So wait, what's D asking? How does that make sense with what we're doing? How do you find volume? You have to think geometry, don't you? Area of the base. Area of the base times the height. True. What's the volume of the cylinder? Pi squared h, right? So we need the area of the base, and then we need that accumulated. Ooh, accumulation. That's what integrals do. Accumulated through. So what's my area of my base on this one? Oh, it's always changing. I know. What's the variable expression for the area of my base? What's always changing? R. And what's the area of my base? Pi r squared. So what could I do to find the volume? Do I need an integral? No, I just need geometry signs. Right? So wouldn't it be pi whose square? R of h squared times h. Oh, no. Really? So it wasn't like a complicated plugging into a formula? It was actually like a logical, just making sense of it all? Wait, but how do we make sense of it all? What's going on down here? Can you guys see it? I know there's an integral expression. I know I kind of brought in that FRQ a little bit early since we are literally in the first section of integration this year. But what do you guys see that they did? They're using integration, but how are they using integration? They have our r, they have it from 0 to 10. Why? Why doesn't our formula work perfectly? Why would this just be an approximate instead of an actual?
Because that's the radius just for that initial thing.
This all is fine, because it is the area of each and every one. But question, what does this do? Doesn't this need to be... How long is the radius? For instance, if I was to plug in h is 0, h is 0.1, h is 0.2, h is 2, and 3, and 7, and 9. How long is the radius, whatever those amounts are? For what interval of h? Yeah, always change it from 0 to 10, but let's say I was to ask you the radius at something like 5. Okay, if you were to plug in 5, you could do 3 plus 25 is 28, 28 20ths. For how long is the radius 28 20ths? Only at 5. And question, what kind of depth does 5 have? None, right? So I can't just use h. What I need to use is dh, because dh makes them infinitesimally thin and accumulates them throughout. So the idea is right, pi r squared times h. But what's the h for each and every r? 0. Because each and every r, 5 doesn't have any depth. 5 doesn't have any height. There's 4.999 or 4.9 or 4.8 or 4.7. You did a 7 point whatever or 9 point whatever. Each and every radius has absolutely no height to multiply it by, so what does an integral do? It says, okay, I'll give you a little bit of depth, which automatically approximates. And when we automatically approximate, we'll throw that in an integral. Everything gets perfect. And those weird discs and washers that you guys thought of last year, which we're going to definitely, don't worry, get to and take time on. Instead of having error, why am I showing you this? What do Riemann sums do? Don't they give error? So the same way that Riemann sums give error, discs give error, pi r squared h would give error, but when we throw an integral and a dh, we make an infinitesimal within and accumulate that whole idea of infinite sum instead of finite sum, then we'll get it perfect. So, long story short, to get the perfect volume, could you have avoided an integral? No. You needed an integral to be perfect. Could we have approximated? Yes, we could have approximated with a finite sum. We could have estimated, but we needed an integral to be perfect. And as you guys saw, what were they asking for? Estimated or perfect? Yeah, they were asking for perfect. So an integral was necessary. However, the idea was just the geometric sense of needing to accumulate. Let's see. We're not doing the infinite sums quite yet. We're not doing them perfectly quite yet. But you are going to have some basic integral stuff coming into play. For instance, what do you guys see here? How are you going to be able to do these without, or how are you supposed to be able to do these without even using antiderivatives? Yes, the AP would do something like, hey, from 0 to 1 of f of x, they wouldn't give you x cubed. There's no way they would give you that. They would give you an f and they'd say, hey, f of x minus 2, or 1 minus f of x, right? So how could you solve each of these without actually antideriving?
Using the properties.
Oh, what about the properties?
Can you combine 1 and 0?
What do we know about x cubed? Use odd. How does that help us with going from -1 to 1? 0. That's easy. How about 52? It's an area. And the area got what? No. This one got moved 2 to the right. So therefore, all my bounds, okay, plus 2 would be 2, and plus 2 would be 3, from 2 to 3. Whew, that's the exact same thing. I'm lucky. It got moved 2 to the right, so did my bounds. But this one didn't get moved right or left. It got moved up. And as soon as it got moved up, whatever area was there from 0 to 1, I don't care about it much, besides the fact that now it's on top of this, wherever it was. So if it's on top of this, whatever that 1/4 was, what's down here? 3 times 1 is 3, so 3 plus 1/4 is going to end up being my final answer. Ryan, do you have a question?
Yeah. Shouldn't area be like absolute value always? It's just like a value. And even if it goes into the negative, it's still a shape.
Except you're taking the geometric definition of area and you're applying it to our application of area in, I'll just say in calculus for right now. So what I have been saying multiple times today is the change in the antiderivative or the change in the original function, because I am reminding you, as I remind you, that we're using area to answer a bigger problem of change in the and change can be positive or negative. So my area, which is always positive when applied to calculus, will be sometimes subtracted, sometimes added in a way where it could be positive. Does that make sense?
Yeah.
So area is just one piece of the puzzle. It's not the final end all. AJ.
How was the difference still
Because check it. Lorenzo, were you the one saying the shifting? It shifted right to. And aren't these x bounds? So when I go right to, the x ends up adding to and adding to. So 0 plus 2 would be at 2, and 1 plus 2 would be at 3. So whatever used to be here, between, for instance, 0 and 1, just got moved. So the exact same thing is now over here. Oops. 0 to 1. Yeah. Got moved over here from 0 to 1 to 2 to 3. So it's the exact same thing, aka with the exact same area. Whatever the shape is, I'm not actually drawing the shape itself. Sorry, I'm doing the AP version and you wouldn't know what it looks like. X cubed would technically be like this, but it just got moved. So it's the exact same thing. And so, oh, yeah. What happens when I have an absolute value on the inside? Absolute value on the outside, the y's flip out. Absolute value on the inside. Instead of a vertical flip, it's a horizontal flip. So what was on one side is also on the other. So therefore, I have it's a reflection of whatever was here, now over here. So you have kind of like an even instead of an odd. It got flipped over. Is it getting a little harder as we go? Let's go with number 55. Yeah. It had a flip and then it also had a shift. Now, this kind of brings in with something that we have to consider the order of operations or the order of transformations. So up one and flipping. Is it going to make a difference if I go up one and then flip it, or if I flip it and then go up one? You sure? Up one, flip, or flip and up one. One ends up and the other one ends down, right? So what does this one end up doing? Does it go up or does it go down? Now, if worst comes to worst, just redoing all the pre-calculations, technically plug each other, since you have the function. It's worst comes to worst. Now, I know we have antiderivatives, and I know we can solve, but remember, I'm preparing you for the AP questions where you will have no idea. Now, there is something crazy, though. Couldn't we technically just, knowing the properties of antiderivatives, couldn't we make it look like, right? So we could go worrying about what the actual function looks like and exactly what transformation ended up happening. We could go ahead and figure out, okay, if we plug in -1 or 0 or 1, where is this function actually at? We could do that. But with properties of integrals, we don't have to. Because isn't this just going to be a rectangle, a 1 by 1? And then this one, we already know what it is, because it's 1/4, we end up just with 3/4. So we could avoid the whole issue of which transformation occurs first. And instead be like, well, shifting up 1, that gives us a box. An additional 1, and then we have that little 1/4 that's actually going to end up below. This one technically is a flip and then an up 1. How about 56? My bounds are funny. And then an absolute value on the inside? Huh. I did 1 dx and then minus x cubed dx. And then, no, just dx. Just dx. Have you guys figured out 56 yet? So soon? You guys forgot what to do with absolute value when you don't know? Hey, come on. Out of anything that we've done this year, piecewise functions with absolute value is one of the ones you've seen the most, right? So what can we do? I heard it. Someone said, split the bounds. Can I go from -1 to 0? From 0 to 2? What's going to happen from -1 to 0? Which guy is it? Negative x. So I'm going to have a -x minus 1. Which, if that's cubed, can't I just pull it out? And then plus, because area adds. If I have the area of one shape plus the area of the other. From 0 to 2 is just going to be x minus 1. So now what?
This one, shouldn't the first one where you put out the negative, shouldn't it be x plus 1?
Oh, did I just pull out one off the other? Yeah. Guys, what happens when I have a negative? I could put the bounds. I don't know if that would necessarily help anything. Would it help anything? I think I just have a shift to the left. Hey, I have a shift to the left, which means AJ back to the bounds. My bounds will have shifted. Oh, okay. So it's the exact same area shifted to the left, except what happened to it? Okay, so that's going to be negative 1/4. Because 0 minus 1 is going to be negative 1. 1 minus 1 is 0. So it's this exact same 1/4 shifted to the left, but multiplied by a negative. Got it. How do I do the next one? It got moved to the right one, so I have to add 1. Okay, well that's 0 plus 1 and then 1 plus 1. Well, wait. That's just 1 to 2. This is 0 to 2. Wait a minute. What if I took this out? Wouldn't this be the exact same thing? Check it. As negative 1 to 1 of x cubed, which is just 0. Because my 0 to 1, if it gets shifted 1 to the right, that would be 1 to 2. But then I'm like, wait a minute, but before it was shifted, then that would have had to go an extra, where was he, an extra 0 to 1? So if I plug in my minus 1, that'd be 1, and minus 1, negative 1. Oh, it's negative 1 to 1 of that was 0. Plug it in, plug it in. Ugh. Okay, so there's some nasty things that might show up. That one, yes, I know you could have anti-derived, but once again, the AP might not have given you F. The other thing you guys might see in homework is just MVT coming back with a perfect rectangle. But I don't really remember if you guys see it in homework or not. Just kind of be aware. There might be an MVT that shows up, and then the general anti-derivative, but don't stress too much. Let's try homework and see what we're able to do with Riemann sums.
Oh my
Yeah.
gosh. Can I borrow a band-aid? Can I have a band-aid?
Yeah, do you need a wipey thing too?
Yeah. I'm kind of cut my stomach.
Wait, what happened?
You guys ain't cutting yourself.